Hello and welcome to Position, Velocity, and Acceleration Lab. This lab is going to be conducted with an instrument called the motion detector. This is a Go motion detector made by Vernier software, and it connects directly to the computer. And the way this works is very much the same way that your autofocus on this camera works. And that is, it sends out an ultrasonic, which means above sonic pulse of sound, which then reflects off of an ear object and comes back, and it's detected by this detector. And so this detector assumes it knows what the speed of sound in this room is, and knowing the velocity that the packet of sound is traveling at, the speed of sound, and knowing how long it took to get out there and back, it calculates the distance to the object that the sound reflected off of. Now, it doesn't just do this once to determine the position. It does it many, many times to determine if that position is changing. If the position is changing, then that distance will increase or decrease as the object moves back and forth in front of the detector. And because this knows the rate at which it is receiving data, it can measure a change in distance over that predetermined elapsed time and calculate a velocity. So it can determine velocities this way. Now, it also does some other mathematical operations and tries to determine if that velocity is changing with time. And if the velocity is changing with time, then it calculates an acceleration. Now, in activities 1 and 2 of this lab, you'll be moving back and forth in front of the motion sensor while you watch a graphical representation of your motion on the computer screen. I'm not going to show you that here because I don't want to spoil the surprise. But you will be noting the relationships between position, velocity, and acceleration by examining their relation in a graphical sense. Now, in the last activity, you'll be looking at a constant acceleration. And for that, we're going to use this cart. Before we move on to activity 3, I want to talk to you about the curve fitting functions of Logger Pro. Now, Logger Pro is the graphical analysis software that we're going to use to apply mathematical models to the data that we acquire. And so our motion sensor will pick up position information and how that changes with time, and that information is sent to the computer and it plots it in a graphical sense. And so this is the way a lot of times that physics works with reference to mathematical modeling, is we look at a sequence of data as we plot two variables against each other and say, you know what, this looks linear, or this appears quadratic. And so therefore, we then try to fit our data to that mathematical function and then use that mathematical function to predict future data acquisition events. And that's called mathematical modeling or graphical modeling. Now, the relationship between position, velocity, and acceleration are an ideal example of mathematical modeling. You see here's the equation that we've come up with to model distance with respect to time. The two variables we're looking at are distance, d, and time, t. And you see that distance is equal to 1/2 acceleration times time squared, plus initial velocity times time, plus an initial distance. And so what this tells us is that the way distance varies with time is a quadratic equation, where the parameters are 1/2 a in front of the t squared, v naught in front of the t, and then d naught. Here's another equation that relates velocity as a function of time. V is equal to acceleration times time plus initial velocity, v naught. And so this is obviously a linear equation in the form y is equal to mx plus b, where v and t are the two variables. Now, one interesting thing to note, if you take a look at this quadratic equation, if you have position changing with time, but there's no acceleration, this acceleration is 0. This term goes away, and you're left with position is equal to v naught t plus d naught, which is, just like that, a linear equation. So by using a quadratic fit or a linear fit, we can model position and velocity with respect to time, depending on whether there's an acceleration or not. So to complete activity 3, we need a constant acceleration due to gravity. The way we do that, we're not going to drop an object. That would fall much too fast. We want to slow it down a little bit by just putting an object on an incline. And so this is our cart, and it's on an incline. And you see this has this little cell on the front of it. This is so that the motion sensor will be able to detect the cart. And there's a stop down here to keep it from rolling off the track onto the floor. Now let me show you how to connect the motion sensor to the cart. I have this rod here with the motion sensor facing this way. It fits just so. I can put this little thumb screw in there, and at that point I can slide this into place on the track, and now my motion sensor looks down the track at the cart. And so activity 3 has two situations. The first situation, you're releasing the cart in front of the motion sensor and watching its motion as it accelerates down the track. It has constant acceleration down the track. But then situation 2 is a little bit tricky. You're watching the acceleration of the cart as it goes up and back down the track. And you have to determine, is the acceleration always positive? Is it going from positive to negative? Is it always negative? Those are some questions that you'll answer in situation 2 of activity 3. So have fun.